Hello guys and welcome back. In this lecture we're going to talk about combinational logic. Now there is two types of logic. One of them is called combinational, the other is called sequential. And we're going to go deeper and explain each of these types and see what are the differences in between them. So let us get started. So we have already talked a bit about combinational logic in the introduction section. We have talked about the logic gates, which they have some inputs and an output, and depending on the combination of inputs we will get an output, right? I mean, we have already mentioned the super basic gates like the AND gates, OR gates, and now we're going to mention also the NOT gates. These are the most basic gates that you will find in logic design. So if you remember, the AND gate had this truth table where the only way to get an output of 1, where the only way to get an output of 1 is to have input A and B being 1. Otherwise, if A is 1, B is 0, we're going to get 0. Same thing for 0, 1, same thing for 0, 0. All of these we will get 0 at the output. So if you connect the lamp right here, the only way that you will have this lamp lighting is when both of these inputs are 1, meaning there is a voltage on both of these inputs. The OR gates, we have also talked about it, and we have said that we can always get an output of 1 unless A and B are 0, right? So if A and B are 0, we will get no light at the bulb if we connect the bulb right here. Otherwise, if either of these is 1, or meaning if either of these have voltage, an output here will be 1, meaning the bulb will light. Now the last type we're going to talk about here is the NOT gate, and it is actually what the name says, it is a NOT. So if you give it a 0, it will give you a 1. If you give it a 1 at the input, it will give you a 0 at the output, right? So if you give a voltage at the input, you'll get no voltage at the output, and vice versa. Hello guys and welcome back. Now let us design some circuits using an OR gauge that we have learned about. So let us take this example. We have already talked about the switches before, and we know that the basis of all of this logic design is switching. So assume that we have an energy source here connected in series right here, and we have a load right here. And this load could be a bulb, it could be actually a motor, anything that we can turn on and off. Now let us analyze this circuit. We know that whenever we see parallel lines or parallel switches, this is an OR gate. So we can combine this and we can say, okay, this is an OR gate. Now, do we see any other parallel lines? Actually, no. So this is the only OR gate that we have here. Now we can consider these just one line for the moment in order to see what kind of dependencies we have in this circuit. We know that this OR gate is dependent on S3 and S4, meaning this OR gate needs to be giving us a 1, S3 need to be giving us a 1, S4 need to be giving us a 1 in order to have an output of 1, right? So remember, whenever we see dependency, we are talking about AND gate. So we know that these three right here are an AND gate with the 3 inputs. First input is for S4, second input is for S3, and the third input is for the output of the OR gate. Now bear with me, we're going to see this visually in a moment. The last thing that is unusual is that this right here is a closed switch. Well, a closed switch can be represented as a NOT gate. Why? Because now the normal state of the switch is what we consider as 0, right? Now, the normal state of the switch is closed. Whenever the switch is closed, it is conducting power right here and giving us a 1. So the normal state is 0 while closed. It is giving us a 1 at the output, meaning that the input and the output are the exact opposite of each other, meaning this is a NOT gate. Now imagine that we energize this, and this is now an open switch, right? So this is a state of 1. When this switch is open, it's not its normal state, it is its excited state. Well, we have a 1 here, and this is open, meaning we are not conducting any more power, so the output will be 0. So 1 here, meaning 0 here. So this is another proof that this is a NOT gate. Now, how can we combine these 3 gates together in order to get this same switching case? Now, we need one OR gate for these 2, right? So we have S1, S2, and the output will go to the AND gate right here. Now, what does this AND gate contain? It has S3. This is S3, right? So we have S3 and S1 and S2 connected like this. Next, we have this S4, which is a NOT gate. So the input here will be a NOT gate, as we can see, right? And is connected to the AND gate. And then this whole AND gate is connected to the load, right? Now let us compare the functionality if it's working or not. We need either of these switches to be closed. We need S3 to be closed. And then we will have a line of power, right? It's enough for us to have that. So assume that S1 is closed. And this is an OR gate, so the output here is 1. Great, so we have 1 at this AND input. Now remember, the AND gate will give us an output only when all its inputs are 1. So we have guaranteed our first input to be 1 right here. Next, S3. Well, we said we need to close S3, so we need a 1 here. So we have 1 at S3 and 1 here. Great. We need one more 1 in order to get an output. Now, S4 normal state is closed. When it's 0, it's closed, right? So if we put 0 here, we're going to get 1 at the output here. So we have another 1 here. So we have 1 here, 1 here, 1 here, meaning the load is conducting. Now let's take a case where the NOT gate is having a 1. So if we energize this, it's going to be open, and well, the power here should be cut. So if we put 1 at the S4 right here, it's going to be 0 because this is a NOT gate, and this 0 will propagate till here. So we have now a 0 at one of the inputs of the AND gates. Well, this means that there will be no conduction of power because it's an AND gate. And all of these need to be 1. So this circuit is actually working as expected. So let me sum it up. First, you analyze what OR gates you have. And then you analyze all the dependencies that you can see. Here we have S4, S3, and this whole OR gate is combined to one line, right? So we have 1 line, 2 line, 3 lines dependent on each other. So we have a 3-lined AND gate. Then we check what kind of NOTs we have. We have only 1 NOT gate right here. So we just put it at the input, and then we connect the output to the load. Now let us continue with another example. Assume that you're trying to design something, and this is the truth table you have. Assume that you have 3 inputs, and you have 1 output. And these combinations is what you're looking for. If input 2 is 1, you want your output to be 1. Also, when your input 1 is 1, you want your output to be 1. Again, when all the 3 inputs are 1, you want the output to be 1. So you have 3 cases where your output is conducting and resulting in 1. So you have your table and you wrote your logic. Now all you need to do is fill it with all the possibilities. So these represent all the combinations for 3 inputs, right? I mean, you have 3 inputs. So in order to get all the combinations in binary, you need to say 2 to the power 3, meaning 2 to the power number of inputs, and you will get the number of combinations. So 2 to the power 3 is 8. So here we have 1, 2, 3, 4, 5, 6, 7, 8. And this is the possibilities you have. And then you have figured out that, okay, you have 3 of these cases where your output is 1. So what do? You create an OR gate with the number of cases where you have an output of 1. So this is my OR right here, and I have 3 cases right here, right? So I will have OR gate with 1, 2, 3 inputs. See, we're starting from the end and we're going to build up till the beginning where the inputs are. Next, See these input 1, 2, 3, all of these are AND gates. Alright? Because you're saying here that you have three options, any of them is going to give you a 1. And when you say the word any of them, you're talking about an OR gate, right? Now, when you check the combination, you're saying I want input 1 and input 2 and input 3 to be at a certain state. This is why you need an AND gate right here. You need three of them, right? One for this one for this one, and one for this case right here. Next, you're going to identify where you need NOT gates. Now, whenever you see a 0, you're just going to put a NOT gate, right? So in our case right here, we have two NOT gates. In the second case, so this is 1, this is 2. In the second case, we also have two NOT gates because we have two zeros. So we have one here and one here. In the last case, we have no zeros, so we have no NOT gates. None of them. So let us start wiring. The first case, I want input 0 to be 0, input 1 to be 1, and input 3 to be 0. Now what we're going to do is we're going to have input 1, 2, 3 just put like that vertically, and then we're going to distribute these three inputs to all these gates, because all we have is the three inputs, and then they are distributing to these gates. So first we are distributing this to the first case, 0, 1, 0. So this input is going to this NOT gate, input 1, because it's a 0. Input 2 is 1, so we are taking it directly to the AND gate. Input 3 is 0, so we are taking it to this NOT gate, right? Now let us continue with the second case. The second case is saying that input 1 is 1, so let us take, this is input 1. We are going down all the way to this AND gate. See, it's connected directly to the input of the AND gate. Now input 2 is 0, so we need to connect it to a NOT gate, right? So this is input 2, we're going all the way down, and then it's distributing here at the NOT gate, that's great. And then input 3 is 0, this is input 3, you follow it along, you got your input right here, it's going to distribute to a NOT gate, and that's it. Next we have input 1, 2, 3, all of them are 1s, right? So we have no NOT gates here. So this is input 1, 2, 3. As you can see, they are going directly to this gate. Now we connect the NOT gates directly to the AND gates, like that. And then the outputs of all of these AND gates will go to the OR gate. And this is our logic. So, let us sum it up one more time, really quickly. First, you identify where are your 1s at the output. We have 3 1s, meaning we have 3 options. Either of them would give me a 1. Either of them means an OR gate. Next, we check what kind of combination is going to give me each of these 1s. These kind of combinations are AND gates. So I have 1 option, 2, 3 options, so 3 AND gates. Now we check case by case. We have, whenever we see 0, we're going to put a NOT gate at the input. So we have 1, 2 for the first case, 1, 2 for the next case, and the last case we have nothing. Then we just interconnect them all together, and that's it. And by that, we have designed a circuit that can conduct this logic. Now, there are more techniques in order to reduce the number of logic, but right now we're keeping stuff simple. And I just want you to get an intuition on how logic can be designed with circuits. Now, of course, if you wanted to, you can change all of these NOTs and ANDs to switches, right? If you change them to switches, as we have learned before, well, you will have the same logic. It is as simple as that. Hello guys, and welcome back. Now we're going to talk about more complex gates, and we're going to see what are their logic and how do they function. So we're going to talk about two different type of gates, the XOR gate and the XNOR gate. Now the XOR gate is represented with a symbol like the OR gate, but it has an arc behind it. The XNOR gate, the same, it looks like an OR gate, it has an arc behind it, but the difference is it has a circle as well in the front side. So, what does the XOR gate do? It checks if two signals are different than each other. If it is the case, then we will get a 1. The XNOR gate checks if both signals are equal to each other. If it is, then we're going to get an output of 1. So let us take a look here. When we have two different signals, like take a look at the A and B. When we have 0, 1 or 1, 0, we're going to get an output. Otherwise, when the signals are similar, we will get a 0. See here? 0, 1, we're getting a 1. 1, 0, we're getting a 1. If they are similar, we don't get anything. So XOR tells the difference. Now take a look at the XNOR right here. If they are similar, we get an output. So A and B are similar, we get an output of 1. Here they are different, so we get nothing. Here A and B are similar, 1 and 1, so we get a 1. So again, if we take a look, 0, 0, we get a 1. 1, 1, we get a 1 because they are similar. When they are different, we get a 0. So this is very important when you are trying to compare two signals or two numbers. These circuits come in real handy. Now we are still have two more gates that we want to talk about, the NAND gate and the NOR gate. Now the NAND gate looks like an AND, but it has a NOT in front of it. This circle always represents the NOT gate. The NOR gate also looks like an OR, but it has a circle in front of it. Don't confuse it with XOR because XOR has an arc behind it. So, an AND gate is just an AND gate inverted at the output, and it looks like that. See, if you put an AND gate and you have a NOT gate in front of it, you're going to get a NAND gate. And you might ask, why would anyone invent that? What's the use? Well, it turns out that it is easier to design transistors or gates using transistors when you have NAND gates and NOR gates. Because, well, usually the transistor logic is inverted. When you're excited from the input with 1, usually you get a 0 at the output and vice versa. So it's easier to work with NAND and NORs when trying to design real electronic circuits. Next, the NOR gate is just an OR inverted, so it's like you have an OR gate and you have a NOT gate in front of it, and it will be represented like that. And as I said, they are really useful when you try to redesign electronic circuits. We're not going to get into that for now, but just bear in mind if you have this question pop up in your head, like, why would we need a NAND gate or a NOR gate when we already have AND gates and OR gates? Now let's check the truth tables for these. And NAND gate, as you have saw, it's just an AND gate inverted. So if you take the truth table of the AND and you just invert all the output, you're going to get your logic. Because in an AND, the only way to get the 1 is when you have 1 here and 1 here. So 1 here and 1 here, you'll get the 1 at the output if you have an AND gate. In order to invert everything, well, here we're going to have a 0 and everything else we're going to have a 1, because in the AND gate, these three cases will give you a 0 and only this case will give you a 1. So we just invert it. Now, the NOR gate is just an OR with a NOT gate, right? So it is just the OR logic inverted. Now, usually in the OR gate, all of these three cases are 1s, right? Because either of these should be 1 in order to have a 1 at the output. And only this case, when we have both zeros, we will use to get a 0 right here. So this is why we have inverted everything. Now if we have 0, 0, we get a 1. Otherwise, whatever we do, we just get all zeros. Hello guys and welcome back. This lecture, we're going to talk about VHDL. Now, VHDL is a way to program hardware. What does this mean? I'm gonna really explain this to you in very simple words. So, why do we need a hardware-based programming language? What's wrong with C? What's wrong with Python, C++, Java? What's wrong with all of these programming languages? Well, they're great. They can do great software. But VHDL is not really to write software. VHDL is to write hardware. I know the concept could be totally new to you, but it is what it is. When you're using VHDL, you can actually write circuits. That's really an exciting field, and it's vital to understand the small bits of any microcontroller system. Because if you understand how to program a hardware, or how can you design a hardware using programming, you are going to be understanding how microcontroller works. Because, well, a microcontroller is actually all of these small bits of digital hardware packed together. Now, let me introduce this to you in even simpler words. Can you see this? Those are all electronic components. They are digital electronic components. Okay, so this could be a flip-flop, an AND gate, OR gate, XOR gate, a latch. There is a lot of digital components which we will talk about in this section. But as you can see, there is a lot of them. If we count here, at least we would be having around 25 digital electronic IC. Now we call these black things ICs, or integrated circuits, because it's packed multiple small circuits together, so we call it an integrated circuit. In addition to all the other components that this IC needs in order to operate. So every IC needs resistors, capacitors, inductors. There is a lot of stuff going on here, and designing this is really not an easy task. It's not about just interconnecting stuff together. There's a lot of calculations that need to be done here in order to get this circuit to actually work in real life. Well, this makes prototyping any digital system a real nightmare, because digital systems are really complicated. And if you check any small CPU or any microcontroller, you could be finding a million electronic components packed inside it. A million. That's a huge number. Imagine you have thousands of these all packed together in order to test a very small microcontroller. That's crazy. However, what we can do is we can throw all of this away and just get this small chip, which we call FPGA, or Field Programmable Gate Array. Okay, we will throw all of this, and we are going to program every one of these black integrated circuits inside here. So we are going to define AND gates, latches, ALUs, memory sections. We can do whatever we want, and we can pack any digital system we want inside here. That's really huge. Any large company that works with digital electronics use FPGAs, and programming FPGAs is not really straightforward. The learning curve of it is a little bit steep, and we are going to try our best to explain the concepts so that you can go for it. Now, you might ask, well, can't I do this in any microcontroller? The answer is no, because in microcontrollers, you don't get to program the circuits, you don't get to program the timing of the circuits, you don't even get to program real parallel processing. FPGAs can work in parallel, so you could have multiple circuits all working in parallel totally. Now, microcontrollers, as we are going to see, and when we progress, they are executing in a sequential way, instruction by instruction. It's not parallel at all. At best, you could be having multi-threading, which is a semi-parallel process. Okay? I have said a lot of technical terms, maybe that you won't understand for now, but by the end of this course, everything that I said now, you will be able to understand it. Okay? So, in simple words, this FPGA can pack all of these all together inside here. So it's used in order to prototype digital systems, prototype its timing, prototype its constraints. It can do a lot of stuff actually. So, what is VHDL? It is the language that we are going to use, and it is a hardware description language because we use it to write hardware. We use it to program digital circuit. Now, there is another programming language that is also very popular, which is called Verilog. But in our course, we are going to be focusing on VHDL. Hello guys and welcome back. So in this lecture we are going to download the Quartus Web Edition, which we will use in order to write VHD code, and this is where we are going to start with the FPGA and VHDL section. In that section we are going to learn all about programming circuits. So the first thing I want you to do is just type Quartus Web Edition download and go to the FPGA software.intel.com. Click on the link here. Now you will get two versions, Windows and Linux. Make sure you're in Windows and choose version 20.1.
Now, I want you to choose individual files, and I want you to download two files. I want you to click on this download here for Quartus Prime. It's a free edition for Quartus. And I want you to download this Cyclone V device, the V version. Now, these are the supported devices that we will need, and this is the main software. So make sure you download these two files, and maybe you will have to create a new account on the Intel software right here. So in the Intel website, you need to create a new account in order to be able to download any of these. So it's a straightforward process. Just simply create an account and download these two files. Now, after you're done downloading them, I want you to put both of these in one folder like that. So the first file and the second file. It's very important to do that. Now I want you to click on setup.exe, and we are going to install the software, just a straightforward installation process. And make sure that devices here is selected. Now, if you don't have this .qdz in the same directory, you won't be seeing this option, and this is critical. You need to make sure that you have this option in order to be able to compile your files in the Quartus software. So make sure you have this option, and then you need to continue installing this. It's a very straightforward process, actually. Now in the next lecture, we are going to start writing some code.
Now let us have some examples for these complex gates. Assume I wanna compare two numbers if they are equal, and believe me, this small circuit is used everywhere in logic design, everywhere in electronics as well. There is a separate circuit in every CPU that checks this small thing right here. So let's assume that we have two numbers, and I wanna check if they are equal. So how can we check that? Let us design this with XNORs. The black box should look something like that. I have two numbers that I want to compare. Each number is 4 bits, right? So my first number here is 4 bits, A0, A1, A2, A3. And my second number is also 4 bits, B0, B1, B2, B3. And I want the circuit to shoot 1 here at the output if these 4 equals these 4. Otherwise, I want it to shoot 0. Let's see. Now remember, the XNOR gate is the gate that checks if two numbers or two bits are equal, right? So I want to check if this bit equals this bit, this one equals this one equals this one, and this one equals this one. Is that correct? If all of these 4 bits are equal, then, well, I can have an output of 1. So I need 4 XNOR gates to do that, right? 1, 2, and 3, 4. I want to check A0 and B0, A1, B1, A2, B2, and A3, B3. And I'm going to have 4 results right here, right? If those 4 results, all of them have shooted 1, meaning yes, these two are similar, and these two, and these two, and these two, well, then I should be getting an output. So how can I combine a result if all of them together are shooting 1? Well, I need an AND gate. So to combine this result, I'm gonna need an AND gate like that. And here is my output. So this is how I could compare two numbers. I need 4 XNOR gates and 1 AND gate. The XNOR gate is going to compare the individual bits if they are equal. Then if all the individual bits are the same, then I shoot 1. Now, if any of these is not equal, meaning let's say that here I have 1 0 1 0, but here I have 1 0 1 1. So here I have 1 1. It means that this Z3 right here is not going to shoot 1 because, well, these two numbers are not similar. So I will get a 0 right here, meaning that this AND gate will not shoot at all, right? It means that these two numbers are not equal. And by that, we have designed a small circuit in order to compare two numbers.
Hello guys and welcome back.
In this lecture, we're going to start Quartus Lite Edition. I hope that you have installed this from the previous lecture and you know how to install the Quartus Lite Edition. This is the software that we're going to use to program in VHDL, which is the language that is used to program logic gates, that is the language that is used to prototype microprocessors, memories, arithmetic logic units, and a lot of stuff. So we're going to learn the basics of this language, and we're going to see how we can implement logic gates and logic circuits using this software. Now, as we progress through this section, we're going to learn new stuff. So every time we take a new component, we're going to see how we can program it, and at the end, we're going to put everything together to create a small project. So let us get started. So to start with, you need to go to File and you need to go to New Project Wizard. Here we can create our project. We need to click on Next. Let's call our project Project 1. You can call it whatever you want. Click on Yes. This is the directory. Let's click Yes. No, do you want to select a different directory? Let's say No. And we need an empty project. Click on Next. Next. Now, here, I hope that you have installed the library that I've told you to install. If so, you're going to see this family right here. If not, please try to install the device library that we've talked about in the previous lecture. Now, let's choose the Cyclone V, E-base, let's say. Doesn't really matter right now what you select, just select any device randomly, and click on Next, Next, and Finish. So right now we are creating a new project. And here we go. This is our Quartus. Now, there is something that you need to do, which is to set up a simulator. Now, you're going to see what is a simulator later, but for now, I want you to follow these steps. Go to Options, ADA Tools Options, and I want you to put this path. This is the path where we have installed ModelSim Altera. I want you just to put this path exactly as it is, and I want you not to forget adding this Windows 32 ALOEM. Okay? Make sure you've done that. If you want, you can freeze the screen right now, copy this path, and add it to ModelSim Altera. Now, the next step is I want you to go to Assignment and go to Settings. Now, in Settings, I want you to go to Simulation, and I want you to choose ModelSim Altera. And I want you to choose here VHDL, and I want you to click on OK. Alright? Next. Now, by that we have prepared the environment. There's other settings that we need to do later, but for now, that's enough. So, now let us create a new VHDL file. Click on New, and I want you to choose VHDL file. Now, this is an empty file, and this is where our code will go. So, our aim is to create a very simple AND gate. So, it has two inputs and one output, and depending on what input combination we put, we're just going to get an output. So, let us see how we can implement this component. And remember, what we're doing here, we are programming circuits. So, we are programming the circuit itself. So, first, we need to add the libraries. Like any other programming language, we need a library. So we need library IEEE. This is the first library. Now, from this library, I would like to use a certain sublibrary. So this is IEE.std logic 1164, and I want you to click on .all. It means I want everything in this library. Alright, these two lines is going to be in every single VHDL file you're going to add. Next, now there is two sections that I need to create here. First one is called entity, and I'm going to call this project 1 is. Then I'm going to write port. and I will open two parentheses like this, and I'm going to leave it here. And in this section, we're going to add our inputs and outputs. Now, the next one is the architecture behavior. So we're going to write architecture behavioral of, and after of, we're going to put the name of the project, which is project 1. Is. And we're going to write begin. Now, see these two sections? They're going to be also in every VHDL you're going to see. Now, there is two things that I forgot here. You just need to end it. So you're going to type end project 1. So you're ending the entity. And you're going to end the architecture. End behavior. Now it's time that I explain to you what's going on. So, here is the port, meaning you put your inputs and outputs. An AND gate contains two inputs and one output, so I can define them like that. This is input A, and this is input B. And we're going to specify the type, which is in, meaning it's an input. And you need to specify what type of input are you talking about. Remember, in any programming language, there's booleans, there's integers, there's a lot of stuff. In VHDL, we have something called standard logic, and we call it STD logic. Okay? We have defined two inputs. This is the name of the input. This is the type, meaning input. We call it N. And then the type of the input, meaning are we using integers? Are we using STD logic? For now, we are using STD logic. An STD logic is just a 1 bit. It's like a boolean, something like that. Not exactly boolean, but you can think about it like a boolean. Next, we have an output, right? So I have one output. And by the way, VHDL is not letter sensitive. So you can type in capital letter or in small letter. It doesn't really matter. If you define this like this, input A, and you use it right here using like something like that, it's the same thing. It's not really letter sensitive. Okay, next we have output, and we're going to call this out because this is an output, and it's also an STD logic. Okay, so we have two inputs, one output, and this is my AND gate. Now, in the architecture, we're going to define how will this input and output behave. It's very, very simple right here. We're going to say output is actually equal to, and the equal to in this case looks like this, a comparison letter and an equal letter. Okay, so it's equal to input A and input B, right? We are trying to AND the logic between input A and input B. It is as simple as that, and by that we have created a gate. That's really nice. It's as simple as that. Now we can compile and see if we have any errors. So click on this, start compilation. Do you want to save this? Yes. And I want you to save it with the same name that you have put right here. Otherwise, we're going to have some issues. Always name your VHDL as the same as the entity you're calling right here. Don't try to name it something different or you're going to have errors while compiling. This is a very important note. So let us just save this. We are compiling to see if we have any errors. And we have actually some errors. And the reason is, well, even though we have a semicolon after every instruction, the last instruction in the port should not have any semicolon, and the semicolon should be after the parentheses. I know this is a little bit weird, but this is how it is in VHDL. The syntax is a little bit annoying. I can tell you this. Let's go again. And we are done with compilation. That's great. So this is the first part of any VHDL code. Now the next one is to test it. I mean, you have written a code, but how can you even test that, right? To do this, we're going to create something called a waveform. So create a new, and I want you to go all the way to University Program VWF. Now there is two ways to create this, either this or you can create a test bench. But I'm not gonna go through test benches right now. I'm gonna go through something simpler so that you can debug some stuff easier. So let's click on this. And now what I wanna do is I wanna add signals. Now this is where our waveform is going to be, and this is where we add our signals. So right click here, and I want you to click on insert node or bus. Node finder, and next list. After you click on list, you're going to see input 1, input B, and output. I want you to add all of them. If you press this, you're going to add everything. Click OK, OK again, and this is your input and output. Now, there is some configuration that you need to do right here. Go to simulation, simulation settings, and see this restore defaults. I want you to click it. And I want you to delete this. No VOBT and the dash next to it. So just remove it and save. Otherwise, you're going to get some compilation errors. Next, we need to divide this in a way so that we are testing almost every case we can test. Usually in tests, you cannot test everything because, well, in some cases, this is like a huge burden, but in simple cases like these, we can test everything. I mean, in the truth table, we have only 4 cases. 0, 0, right? And 0, 1, 1, 0, and 1, 1. So let's say that this section here is 0, 0, and it is already at 0. Now let's take this section, let's say from here, I'm going to put this as 1. So if you go here and click on this one, the waveform will go up. So this is 0, input A is 0, and now input A is 1. So we are testing 0, 0, and here 1, 0. Now we need 0, 1, right? So here, let's say from this point on, we're going to have a 1. So now we are testing 0, 0, 1, 0, 0, 1. And we need to test 1, 1 as well. So let's take this section right here and we raise it both. So now we have 1, 1. So by that, we are testing every combination of inputs and we're going to see the result at the output. Now, let us hit on this here, run functional simulation. We need to save this, and I want you also to save it with the same name, so project 1. Always save with the same name as your entity. Now we try to compile, and we have some errors. Alright, there is one other configuration that we need to do. And this configuration is the following. Let's go back to Quark and assignment, settings, and I want you to open more EDA netlist writer settings. So right now, let us click on run simulation. If it did not work, I want you to go back to simulation settings and I want you to hit on restore defaults and again delete this. Sometimes this happens. Click on save and I want you to hit on this in order to simulate, complete it. Now we are in simulation. And here we go. This is our AND gate. Let's see if the result is correct. When A is 0 and B is 0, output is 0, right? 1, 1, 0, we get a 0 because this is an AND gate. 0, 1, also a 0. Only when we have 1, 1 at the input, we will get a 1 at the output. So this is how we create an AND gate. And the next lecture, we're going to continue with more stuff. So right now, we have designed the AND gate. And actually, we can design any gate just by changing this keyword. So VHDL supports keywords in order to do combinational logic between inputs, let's say AND or XNOR. By just changing this AND to any of the keywords I just mentioned, you can get the logic you want. So let's say that we want to create an OR gate. All we need to do is change this AND to OR. So this is a 2-input OR gate. Now, we need to save this file separately. So save as. And we're going to call this OR gate. So make sure you call it OR gate. So this is the name of my new file. It's called OR gate. So now if you go to here, Project Navigator, you have hierarchy and you have files. Check the files right here. Now you have two files. One of them is project 1, which is the AND gate, and the other is OR gate, which is called project 1 right now, and that's wrong. We need to rename this as well. So this will be my OR gate. Now remember, the name of the entity should match the name of the file right here, otherwise you'll get compilation errors. This is the first step. Second step, if you have multiple files, you need to choose which file you want to compile. So if you right click on this OR gate, you need to press set as top level entity. And by that, you are compiling the OR gate. If you want to compile the AND gate again, you right click on it and you choose set as top level entity. What this does, it allows a certain file to be compiled. That's great. Now, we have this OR gate ready to be compiled. So let us just click on start compilation. Yes. Another thing that we need to change as well is the end right here. So we need it to be OR gate. So OR gate here, and here as well, behavioral of OR gate. So let me recap. The name of the entity should match the name of the file. The file need to be set as top level. And finally, you need to make sure that your entity and an architecture have the same name. Now we click on compile, and the compilation is done. So right now, let us try to simulate this. Create a new file. We need university program VWF, insert node or bus, node finder, list, and here we have the inputs we have. So click OK. And now all you need to do is simulate the same way. So we have 0, 0. This is my 0, 1, like that. This is my 1, 0. And of course, that's my 1, 1. Now go to simulation settings, restore defaults as usual, and just delete this line right here. Click save, simulate. We need to save the file with the same name, so we're going to call it OR gate. We got an error, it's okay, just go back to simulation settings, restore defaults, delete this, click save, and one more time. And here we go. This is my OR gate. 0, 0 is 0, 1, 0 is 1, 0, 1 is 1, and 1, 1 is 1. That's great. So now let us continue here. So what if I have more inputs than that? Well, that's very simple. Let's say I want to create an XOR gate with 3 inputs. So I just need to add input C. And I need to add here, instead of OR, XOR. And I need to XOR the other input. So I have all of these XORs. And this is input C. And I need to call this XOR gate in these 3 places. Then we need to save this, save as. And we're going to call this XOR VHD. Now, next step, make sure this is a top entity, and then compile. And we're done compiling. Now, quickly, let us create a VWF. And we're going to add nodes, node finder, list. Now we have 3 inputs. And let us create the test bench. We have 3, so we have 8 cases. So first one is 0, 0, 0. Then we have 0, 0, 1.
Then we have 0, 1, 1. So here is 1, and here is 1. Next we have 1, 0, 0. So here we have 1. Then we have 1, 0, 1. 1, 0. And here is my 1. Only on the last bit. Exactly. And now we have 1, 1, 0. This is 1, 1, 0. And lastly, we have 1, 1, 1. So all of these are 1s. So we have 0, 0, 0, first case, 0, 0, 1, second case, 0. So we have 0, 0, 0, first case, 0, 0, 1, second case, 0, 1, 0. We forgot the 0, 1, 0. We're going to add it at the end. Then 0, 1, 1. Then 1, 0, 0. Then 1, 0, 1. Then 1, 1, 0. And 1, 1, 1. And we need the 0, 1, 1. And we need the 0, 1, 0. So this is 0. This is 1. And this is 0. So this is how we have all the combination. Now, let us go to simulation settings, restore defaults, and let's delete this line, click save, and let's go to simulation. Would you like to save this? Yes, I want to call it X or gate, the same as the entity name. Let it compile, we're going to get an error. This is actually kind of a bug in the software. So we need to go back, simulation settings, and restore default one more time and delete this line. Click save, go to compile. Yes. And this is the result. Well, remember, XOR give us a 1 when the signals are different. So 0, 0, 0, they are not different, so it is 0. Now, 0, 0, 1, it's different. Why? Because 0 and 0, well, it's 0. Because it's an XOR. Now, this result of the two signals, XORing them with the third signal with input C, is like 0 XOR 1. It will give us 1. Now, let us XOR the first two signals. 0 and 1, XOR them is 1. But XORing them with the last signal input C is going to give us 1 XOR 1 is 0. See what you need to do here? You XOR every couple on their own. So 1, 0 will give us 1. XORing them with a 0, so 1 XOR 0 is 1. And so on and so forth. Now here 1, 0 will give us 1. XORing them with 1 is 0, that's correct. Now 1 XOR 1 is 0. 0 XOR 0 is actually 0, though that's correct. Now when all of these are 1, we're going to get 1, that's correct. And 0 XOR 1 is 1, and 1 XOR 0 is 1. So that's correct. So as you can see, this is how we create gates. You can go on and create any gate you want the same way. Now in the upcoming lectures, we're going to create some combinational logic together.